Hello, my name is Philip Comella, and today we're going to have a conversation beyond science and religion. Now, the concept of tuning is something we're all familiar with. Everybody understands the concept of tuning musical instruments. In particular, back in the old days, we used to do things such as tune up cars, but apparently with the demise of the carburetor and the rise of fuel injection, tuning cars no longer occurs in that concept, but we understand it. We know that musical instruments must be tuned to sound right. Back in the day, cars were tuned, as we know, to make them run more efficiently. And thinking about like a piano, for example, it's fairly obvious that the piano strings must be tightened in a precise manner to give the right pitch and to harmonize with other instruments. Put differently, even an untutored ear can hear an instrument that is out of tune. It turns out that when we zoom out a little bit, scientists who have studied the universe have discovered a tuning on a completely different level. In fact, the closer scientists have looked, the deeper the fine tuning of the world we live in, of the universe itself, becomes. And what is meant here is that the universe appears to be finely tuned to allow for the possibility of life, which is truly a remarkable finding. Now, this topic of fine tuning covers both science and religion. To religion, the fine tuning of the universe is evidence of an intelligent creator behind the scenes. The scientist, however, observes and notes the same fine tuning features, but is not compelled to associate them with an intelligent being. And in particular, for those who are wondering, in particular, the God of the Bible is not raised as the cause of fine tuning, at least in the scientific viewpoint. And this is where the scientific explanations start hedging towards things like the multiverse or the natural explanation. Today, the concept of fine tuning is probably the number one issue. It's a big topic. And those who are looking for scientific books to read on the topic, there's quite a few classics out there, including The Accidental Universe and The Goldilocks Universe, two different books by Paul Davies. There's The Gigantic Anthropic Cosmological Principle by John Barrow and Frank Tipler, and there's Just Six Numbers by Martin Rees. Now, I'd like to add another book to that list, a newer book, and this book is entitled A Fortunate Universe, Life in a Finely Tuned Cosmos, co-authored by today's guest, Luke Barnes, who I'm happy to say is joining us from Australia, which is probably the farthest I've ever had the farthest destination I've ever had a guest. Now, Luke is the co-author of the book. He's currently a professor of physics. It's at the University of Sydney, right, Luke?
At Western Sydney University.
At West Sydney University. So, Luke, thank you very much for joining us. We had to do quite a job of synchronizing our time zones, but I'm really happy that you're here and to have a little discussion about fine tuning.
Yeah, thanks for having me.
So welcome. So first of all, let's just start from a big picture here. What interests you about this subject? Now, you are widely published on the concept of fine tuning, in addition to the book A Fortunate Universe. What is it about this topic that interests you?
Well, there's a few things. One of the things that really got my interest up about it was actually after I'd started researching it and started giving talks about it. I gave a talk on basically the science of the fine tuning of the universe for life at the place I was working at the time, which was Sydney University. I'm now at Western Sydney University. And so there's a room full of astronomers, and we have our weekly, seminars. You get an expert in, or you have someone local just give, a talk for usually, 50 minutes, and then there's 5 minutes at the end for questions. So I gave a talk, and I deliberately left like a bit more time at the end because I knew there'd be questions. But what I wasn't expecting was I talked for 45 minutes and then everyone in the room sat around for an hour and a half asking questions and debating and talking amongst themselves about what on earth this thing means. I've never seen anything like it before or since, but it just grabs it grabs everyone's attention. You can do the same with a popular level audience. There's a widespread feeling that we have to do something about this. Something weird is going on with this fact that small changes to the properties, the basic fundamental properties of the universe would result in a universe that can't sustain or support life. And yet here we are.
Yeah, well, it's really an amazing topic, and I personally have always been interested in it because it's one of the it's one of those topics that whether you fall on the scientific side of things, the religious side, or somewhere in between, it's a topic, facts that have to be dealt with. And I said in the opening, there's that saying from quantum theory, the Copenhagen interpretation. It says, shut up and calculate. Don't start interpreting or try to interpret what the data is showing you, which doesn't make a lot of sense to some people. And I feel like there's some of that with the fine tuning. It's like, okay, let's just list all the oddities, but let's leave the interpretation to somebody else. Now, you don't do that in this book, which I think makes it, entertaining and sort of a real thoughtful read. But what are you seeing in the scientific community with regard to interpreting what we should take away from all this fine-tuning evidence?
So, as you said in your introduction, there's a couple of views. One of them is the multiverse. Right. How did we land on just the right set of numbers and constants for our universe to allow for life? Well, maybe out there beyond what we can see. There's lots of other universes out there, so to speak, with lots of different other values. And so basically it's a lottery, sure, but the universe bought lots of different tickets. And so the right ticket had to turn up somewhere. There's that view out there. There's the view out there that actually we can't, it seems like these small changes mean something, but actually once we really understand physics, we'll understand that you couldn't have changed that number at all. It'll turn out to be something like pi or something like that, where we'll know the deeper reason why it has to be what it is. I actually find that one brought up more by non-physicists than physicists. There's very few physicists who take that hard line, but they're out there. And thirdly, just the view that we don't, in changing these numbers, we don't know how likely any of the different dial settings are. And so, there's something slightly odd going on here, but we can't say anything improbable or unlikely has happened, or that any particular idea about the universe has been rendered unlikely just because we don't have any of the probabilities we would need to make that conclusion. So that view goes around as well.
Yeah. So let's get a little specific here for a moment before we talk about the multiverse more. And that is, there's all sorts of top 10 fine-tuning features of the universe. And I mentioned Martin Rees. There's another one. There's another book I have here called, I think it's called the nine magic numbers or something. I mean, there's always, okay, these are the ones that really mean something. But which fine-tuning feature of the universe do you feel, or which ones do you feel are the most important or the most noteworthy?
I think there's sort of two that really jump out at me. One of them is something called the cosmological constant. So the short story is, if there was a form of energy, so energy takes various forms around us, heat, light, motion. If there was a form of energy that was associated with space itself, just even in empty space, there was a form of energy that still existed there, and was still there. If the universe expands, there's more space, so there's more energy now, because it's just whenever you make space, you make this form of energy called vacuum energy, because it's there even if there's no particles there, even if there's a vacuum. that form of energy would have a major say on how the universe expands. Does it get faster? Does it slow down? Does it turn around and crunch? Does it do all these things? That number, that propensity is represented by a number called the cosmological constant. And we worked out in 1998, and they won the Nobel Prize for this, various people, including Brian Schmidt, who wrote the foreword to our book, that number is in our universe is not zero. It's there's some number there, so that actually the way our universe expands, it's actually accelerating. A galaxy over there is not only getting further away from us each day, it's moving faster today than it was yesterday. And this number, once you start to think about all the ways that you could in modern physics, in field theories, in all we know about the universe, the way you could put energy into empty space, the way things could add a little bit or even subtract a little bit from this vacuum energy, the fact that we get a value of this vacuum energy which allows for structure to form, galaxies to form, stars to form, planets to form, is actually really rather remarkable. Of the set of possibilities for what that number could have been, how much energy is there in empty space, the cosmological constant, the range which allows life or structure or anything at all interesting to form is remarkably small. The rest of these universes, if the number's too large, they expand so fast that no particle ever interacts with another particle. And if it's too negative, then the universe collapses in a fraction of a second. And so that's a really remarkable case where it seems like there's a lot of fine-tuning going on, because there's a lot of different ways that you could put some energy into empty space, all the sort of quantum fields, as they're called. And it's such a clear case of rendering a universe uninhabitable. It's not, we're not dealing with subtleties of carbon chemistry or anything like that. It's literally nothing will ever touch anything else if you get that number wrong. So that's number one. Number two is just the basic stuff that we're all made out of. If you sort of break us down to the Lego blocks of, as far as we know, there's electrons and there's protons and neutrons, but those are actually made of smaller things called quarks. These are tiny little particles. And one of the properties we know they have is they have a mass. How heavy is it? So if you put a little electron on a little set of scales, obviously that won't really happen, but we know that there's a number there that's really, really small in any,
Right.
pound or kilogram sized unit. What if those numbers have been different? Well, actually, there's some rather remarkable constraints that you've got to put there. You've got to land in just the right section of the possibilities if you want a universe that does anything interesting, like has a periodic table. In other words, you can take the smallest bits and put the quarks together and make protons and neutrons. Put protons and neutrons together, not just to make one kind of thing or a blob of stuff, but structures, all of the, hydrogen, helium, now I've got lithium, beryllium, boron, the whole periodic table of options, that then chemistry, and then all of that works out. It turns out if you mess with these fundamental parameters just a little bit, these masses, you end up with a universe where periodic table just doesn't work. You can only make one type of element and it won't stick to itself, or it'll only make one type of molecule. Just the whole of chemistry collapses one element and one molecule.
Yeah, those are big ones, and the cosmological constant. The reading that I've done, I think there's quite a few noteworthy physicists who call that, the most remarkable fact of the universe, or something, the hardest to explain fact. I think even Steven Weinberg is famous for that, for saying that, something that he can't figure out. And just to be clear, under the laws of physics, the vacuum is supposed to have energy because of quantum theory. And when scientists add up all of that vacuum energy, there's a mismatch between what that number is and what is actually measured. Is that correct?
Not quite. So imagine, almost.
Okay.
Imagine you've got a bank account and you're allowed to put money into it or take money out of it. So it's got an overdraw feature, positive or negative. And there's 20 different people who can take money in or out of that bank account. And over the course of a month, they're all, you know, billionaires. So someone puts in something of order of $1 billion, and someone's taking out of order of $1 billion, this, that, and the other, right? So it's wherever it started at the end of the last month. Over the course of a month, 20 different people have either have put in billions or taken out billions without ever talking to each other. And then you look at your account statement at the end of the month, and it says 1 cent.
Yeah.
That's where we are, right? There's
Yeah.
all these different things that could add or take away from, or make negative or positive, the energy of that field. And it's not impossible that it could land at 1 cent,
Right.
but it just, you know, if it wasn't perfectly balanced, then we wouldn't be here. You know, 5 cents and you blow the universe up, -5 cents and you collapse the universe, and all the other values are just completely finished. And I've said $1 billion, so 1 cent to $1 billion is, you know, a billion is 10 to the 9, and we're down to the cents, so that's 10 to the 11. For the cosmological constant, the number is something like 10 to the power of 120, or at least 10 to the power of 100. So it's,
right.
you know, this bank account, there's 20 different people putting in and out trillions of trillions of trillions of trillions. And then at the end of the day, here we are in a universe where that account has 1 cent in it. It's just, that's the sort of weirdness we see around us.
Yeah, and of course, and as you say, that number has to be in a certain range, a very narrow range,
Yeah.
for structures, for galaxies to form, and for everything sort of to hold together. So that we have,
Yeah.
so that we have something that isn't you know, cast to the four winds, or something that isn't condensed and you know, the big crunch, so to speak. And so that is, you know, and frankly, one question that comes up, and that's just one of the many, but one question comes up, and you sort of go there in your book, although I'm really not sure, you know, how far down that road, but you know, at what point do these coincidences or fine-tuning features, whatever you want to call them, build up, where you sort of take a step back? I think Fred Hoyle said this, where it's like a put-up job. You know, something is going on behind the scenes, and you know, I think, and you know, you had a good-natured debate with your co-author in this book about you know, what does it all mean, which is the fun part of the conversation. And so, in terms of, you know, your own views, as a scientist and somebody that's, you know, professor of physics, how do you approach this put up job issue? This, you know, something must be going on. I mean, how do you view this yourself? And then we could talk about the scientific community.
Well, so there's a couple of things. For the multiverse explanation, the thing that I want it to do is to produce predictions so that I can go and test them. Now, I've written papers to try and sort of coax some predictions out of this idea. It's remarkably hard to do. But that's what I want, because that's a way the universe could be. And so what I want to know from that idea is, you know, don't just tell me that it'll solve everything and try to leave it at that. Give me some predictions that I can go and test, or at least a model I could try and derive some predictions from. It's not particularly easy to do. I should say I come to this as a theist, and so there's that resource there always to. I think we'll find sort of fine tuning at the bottom of the universe no matter what, but exactly where it is what I want to know. Is it these parameters or deeper ones? Just because I think there's more ways for a universe to be boring and lifeless than there are for it to be interesting and morally meaningful. And so I think there's always going to be that sort of fine tuning at the bottom, that you'll get a better explanation of the fundamental features of the universe via a reason than via well, no reason at all, or some deeper mathematical principle.
Yeah, and I think that the you know, the multiverse is definitely an option, and I haven't done a poll, but there's quite a few sort of supporters of the multiverse principle. And you know, one of the themes of this show and my own writing, is that there is this visceral reaction that many scientists have against being associated with anything that's even close to religion. And it's sort of my I go back to like Darwin, where Darwin was fighting the church, and that was like the enemy, the opponent in this debate. And I think that the way you approached it is I think more open-minded, and I think that there's not a lot of people that I speak to on this show that are real biblical literalists. They're not the strict constructionists. There are folks that are sort of looking open-minded, trying to look at things in a different way. One of the things about the multiverse that I would ask, first of all, I don't think it's a theory. I think it's, I'm of the real skeptical camp. But if the multiverse is a thing, then wouldn't one of those universes be one in which Jesus Christ rose from the dead, and Moses parted the Red Sea, and all these miracles occurred? I mean, different miracles. I mean, I think when you go to the multiverse, how do you rule out a spiritual or whatever, however you want to put the word, a theistic element to it? And I don't think you can be principled and say, okay, multiverses are only those in which none of them have any spiritual element in them at all. It just seems to me to be, just too much to follow. So have you ever gone down that road about, restricting the multiverse explanation?
Yeah, so this is famously what you need is something called a measure. This is called the measure problem. What that means in the context of physics is you need some way of saying that, okay, possibilities are cheap. Right. There is, make enough universes, and there's one universe out there where some guy stands in front of the ocean or the sea, parts his hands, and at just the right time, whatever else happens, the sea actually parts. Right? What you need is some way of putting a set of probabilities on things. So sure, if that's possible, great. But if it's very unlikely, then you feel like you've still explained something. And so the fact that more things are probable in the multiverse wouldn't immediately destroy its ability to predict things, as long as you've got probabilities. So as long as you can say, I wouldn't expect to be in a universe in which, Moses parted the Red Sea purely just by accident. It was just a coincidence. And so, but the problem here is, and this is going to sound simplistic, but I think it's really getting to the heart of it. A lot of these theories want to appeal to infinities. There's an infinite number of other universes out there. And it's been pointed out, there's a very good and very rigorous paper on this by a guy's nickname, I think is Olum, O-L-U-M. We can go and look that up if you want. Just pointing out that, okay, one of the things that we might expect to be true in that universe is that I'm as much of an observer as you are. So whatever probabilities I assign to things, you should also assign to things. But if you have an infinite number of observers, it's very hard to find a way of assigning probabilities that hands things out equally to an infinite number of people. So this is the measure problem. How do you weigh up different perspective, different observers? And there's a very good argument to be made that it's just simply not possible. But you can't say, if for every 100 times that someone like Moses goes to the Red Sea, does this and nothing happens, one out of those times he goes like this and the Red Sea parts, then you can say, okay, 100 to 1, that's not going to happen. But if it's an infinite number of Moseses and an infinite number of failed Moseses, then how do you say that there's more likely one over the other? Well, you can do that in probability theory. It's just that you need a measure which applies in all these places, but you can't make a measure that honors this any observer is as good as any other observer principle that you seem to need to have there. So there's a real mystery here about how you do physics at all in an infinite universe, let alone an infinite multiverse. So these are why I say I've got a paper out called a reasonable little question about the fine tuning argument. Just my critique of the multiverse is just that it's a toy model at the moment. There's the idea of how you might make these things happen, but in detail, there's an awful lot of unsolved problems that seem very, very formidable for getting any sort of predictions out of these ideas.
Yeah, I just don't find the multiverse satisfying. And I think that's sort of, I mean, it is, it's got so many speculative elements to it. It's just, well, I could be more direct, and I think it really is sort of an intellectual, sort of gamesmanship, maybe is one word,
Mm.
but or maybe it's a maybe it's a placeholder until someone comes up with something better or different. But if you look at it from the perspective of, do you go with something that is in the theist realm, or something where you maybe open the door a little bit for some intelligence somewhere, or do you just put all your cards, all your chips on the multiverse? I mean, you know, I'm a big fan that, evidence, test results, that's that's the power of science. You have to
Mm.
be able to have a testable theory. But the one of the wonders of the fine tuning topic is that it brings up these topics,
Mm,
and
yeah.
it really, it opens the door to you could have an intelligent discussion on this. And I'm not gonna I mean, I think there's an intelligence, but I'm not an intelligent design person, and I'm not a biblical, strict constructionist. I mean, I like to be open minded, but I think, when the evidence points to to this fine tuning. I mean, we haven't even talked about, for example, the low entropy
Mm.
of the Big Bang, and I think that's an amazing, um, story. And I don't know how much you've read Brian Greene, but he's got one book. And I don't. It's not the Elegant Universe. It came after that. It's on my shelf
The
behind
Fabric
me.
of the Cosmos.
Yeah, yeah. It could be. It could be where he says that he talks. He basically says that, um that the universe must have been in a low entropy state at the Big Bang, because according to the second law of thermodynamics, you're going to have more disorder going forward in time. So therefore, you have to start with a low entropy state, which of
Hmm.
course begs the question: what are we talking about here? I mean, how can you have a low entropy state, talking about finely tuned? But then a recent book, and I think his most recent book, I think Till the End of Time, he seems to have changed, and he starts talking about gravity being the force that is sort of organizing everything. But regardless, I mean, I was first sort of alerted to this low entropy issue when I read the Brian Greene book, and I thought he did a good job just facing it head on. But talking about something that is bizarre, um, and I don't know what you make of it. I know you talk about it in your book. Um, you sort of have to say, okay, so how do you wind up with something low entropy or higher order early,
Yeah.
when what's causing that? I mean, so what's your take on the whole low entropy issue?
Yeah. So very quickly, the problem is we see around us that um, to translate the word entropy, what it means is that some forms of energy are useful in that it's easy to convert them into another form of energy, and some forms of energy are more useless. It's hard to convert them into another form of energy. If I had a match here, there's chemical energy in the head of the match. It's very easy to convert that into fire. You just got to strike it on the side of the box, and there it is, fire. Um, but once it's burnt down to the ashes, it would be extremely difficult to get all the energy back and get it back into constituting that match head again. That's basically the second law of thermodynamics at work. Energy becomes more useless, very roughly. And so the question then is, all right, if that's the way our universe works, then there must have been a whole lot of very useful energy right at the start. And that's exactly what we see. There's the form of the energy in the early universe is in a form where it's ready to make stuff. Basically, it's the fact that the universe is almost perfectly smooth, so that gravity can collapse things to make stars, planets, galaxies, suns fire up and stars fire up and make chemical elements and provide energy. All that happens because the universe starts off ready to go. The flip side of that is what it would look like for a universe to be born in sort of ashes. Well, if gravity is the main thing that matters there, it would be black holes. Just you make a universe full of black holes and nothing else happens. The only thing that can happen in that universe is one black hole eats another. That's it.
Right.
And so how did the universe get to have lots of useful energy really early? And you say, oh, maybe that's the way it was born. The problem is the way we understand the second law on a fundamental level is it's not a basic law of nature. All it really is that the stuff around us is undergoing constantly transformations from the less likely arrangements to more likely arrangements. There's just more ways to have the energy that was in that match head spread out over ash and light and heat, and there's more ways to do that and spread it all out than there is to have it contained in that match head. So it looks like, as well as being really useful, the early universe is really unlikely. There's something very special in some sense about that arrangement. The thing that it's an interesting case of fine tuning, because it looks like a case of fine tuning. Like the universe had to be in a very specific state in order for anything useful to happen afterwards. And if anything, this entropy case is a great example of nothing interesting will happen if you don't get this right. All you'll have is black holes, great big black holes, and they'll occasionally collide, or probably even not. They just spread out in empty space. If you want anything interesting, you better have a second law of thermodynamics. The difference is there's something very simple to specify about that early state of the universe if you want it to be useful. So if you could at least imagine some sort of law that sorted it out. Maybe you could imagine it. It's at least simple to specify. The problem with the cosmological constant is, especially relative to the way physics is at higher energy states. That's a hard thing to explain, but anyway. It's not just that you have to hit a small target; it's that target's kind of in the middle of nowhere in terms of the way physics is laid out in the early universe. The fine tuning you would have to do to get the cosmological right today involves a whole lot of coincidences that have no other reasonable explanation in the early universe. Whereas the entropy, it's just got to be low. Now, the problem is low entropy seem like the least likely ones, but at least it's easy to specify what that constraint is supposed to be. So it's an interesting one. When I discuss this, I'm less likely to present it as a case of fine tuning and more a case of, okay, you've been told for at least the last 100 and something years that the way our universe is that it's that order came from chaos, that it started off a complete mess, and then thankfully the laws of science were here to sort everything out, and that the universe just looks like an accident. It's just sort of here, and some random bang, and then here we are. And that's absolutely not the story of science. It's order from the first millisecond. It's just the universe starts in a highly ordered state. That's the initial condition we've got to put in to understand the universe. Maybe there's more to be said about that, but it's certainly not the case that the more science is discovered, the more accidental and random it looks. No, the further back in time we go, the more orderly it is and has to be.
Well, I mean, I personally think that that's a contradiction in the way the Big Bang is presented, and maybe it's just the nomenclature. Big Bang conjures up an explosion, and even though maybe it's not really an explosion, but explosions are chaotic events, and so you're sort of like, it's like a brain twister. You got to like, okay, well, it was really an ordered explosion, which sounds worse in many ways.
Yeah.
So it's one of those conundrums, and I think that to me it's related a little bit to the inflationary Big Bang. I mean, yeah, the inflationary Big Bang, which is an amazing theory in and of itself, and we'll touch on that briefly here because I think it's it's another really weird feature of today's scientific mainstream, where we have the flat universe, the balance between gravity and the repulsive force of the Big Bang, and why is the universe flat when it should have when it maybe it should have contracted, and maybe it should have flown away to the seven winds, and all that, and then the inflationary Big Bang comes along, and which is the standard way to explain the smoothness, flatness, horizon problems. But I had Paul Steinhardt on the show a number of years ago, and I got him on the show because he had written an article in Scientific American about how the inflationary Big Bang was actually more finely tuned than the original Big Bang, and and you touch upon that in your book, which is another, for our listeners, it's an interesting thing, because it sounds really cool. This, the universe inflates by trillions of times, and then the inflation stops, and then it just goes along its normal path or whatever. But then that inflationary event has to be finely tuned. So what are your thoughts about the inflationary Big Bang theory? And I may have butchered some of it, but what can I say?
No, that's about right. There's
Yeah.
in any physical theory, you've got to have initial conditions, right? So the laws of nature as we know them don't tell us how the universe is, they tell us how the universe changes. So if you want to know how the universe is today, you need to know how it was at some point in the past. So, for example, if I tell you where all the planets were last night and I'd give you the laws of gravity, given a bit of work, also not just where the planets are, how they're moving as well, it also matters. How fast they're moving, in what direction. You can then make your prediction. So at some point, you just have to lay down initial conditions. The problem was with the Big Bang theory, and I should say, given what you said earlier, that the name Big Bang was made up by one of the opponents of the Big Bang theory.
Yeah.
It was originally called like the primeval atom theory, but that didn't catch on. And then Fred Hoyle called it the Big Bang theory.
Right.
He did like a radio interview to make fun of it, and it stuck.
Yeah.
And there was a massive competition by Tim Ferriss in the 80s, I think, to try and find a better name, and they still couldn't find one.
Yeah.
Anyway, so don't take the explosion bit too literally.
Right.
But when we thought about the initial conditions there was something that was just a bit odd about them, and you've got to lay them down anyway. But it seemed like you needed to provide some really specific features of those initial conditions where there's no reason why they would be this way rather than that way. So this idea of inflation came along as a way of providing what looked like more generic initial conditions. But arguably, in terms of there's something to be said for that. There's something to be said for that theory. It's interesting that some of the features of the Big Bang theory you could sort of make look more natural and more normal via this process. You just blow the universe up really quickly, really early, and suddenly, hey presto, it looks a bit more like our universe. In terms of the entropy problem, though, because the whole point is that the further you go back in time, the more special you need your initial conditions to be. Inflation is not an exception to that. There's some great articles, there are great sort of scientific papers on this, arguing exactly this point, that that if the second law still holds, then you're still explaining every explanation of a later state in terms of an earlier state has to be of the form of the earlier state is something special, something more fine-tuned, so to speak. Maybe I shouldn't use that terminology there because that's begging the question. More low entropy, more sort of special in the context of the way that possibilities could have been, and inflation's no exception to that. So yeah, that inflation is sort of, it seems like part of the puzzle, part of the puzzle's fallen into place, but it's just raised more questions, at least for me.
Yeah, and I on that note, it's similar. It's similar to the multiverse. So, because it does raise a lot of questions, but it's a fascinating collection of theories, and we're not going to have time to go through all of them because there's quite a number of them. We haven't talked about dark matter, for example, but one of the things I want to ask you before we call it a day is, having studied this problem for decades now, I take it, Luke. Where do you think science is going to be in 25 years or so with this? Do you think there's going to be, I mean, what's your guess on where things are heading? Is
That's a
there going
very
to be
good question. That's a very good question. We're starting to come up against a couple of limits. I mean, it's been perfectly obvious that you can only discover something about the universe if it's there and if it's in a sort of state where it's discoverable. So we're very much reliant on the universe being nice to us at some level.
Yeah.
There could have been a cosmological constant, but it was so small that we never discover it, or at least not for another billion years of observations or something. We're in a little bit of a weird area where we've just spent, particle physics is just, 10 years ago, the Large Hadron Collider, which was billions of dollars. It's a 27-kilometer loop under Switzerland and France.
Right.
And there's talk of what the next one's going to be, but that's going to be an enormous project that takes even longer. And the fact that the Large Hadron Collider did like one of the things we were hoping it would do, but not much else. Like what are we going to learn? We might build something enormous and run it for years and billions of dollars and just find that the ideas we had about the universe are still doing fine at that slightly higher energy level. We've also just put the James Webb Telescope in space, which is, again, enormous, decades of work, billions of dollars. And it's doing interesting stuff. I think astronomy is in a much better area for, if you make something really big, it will at least take some really nice pictures of the universe.
Yeah, true.
But we're just coming up against like the sort of things we need to do in the future to push science forward. We're way past the one nation or one government can do it on their own. We need massive collaborations, and there's no guarantees of success. And we're sort of pushing up, like, there's a limit. We're starting to push up against like geological limits for the biggest collider you can make. And we're starting to think of, okay, could we put a telescope on the backside of the moon? Like, is that an option? So, and people are seriously thinking about that.
Yeah.
It would be exciting and wonderful, but we're just the whole let's get a couple of governments together and get $20 million, and that era is gone. You need billions to do anything. So where we'll be in 25 years is desperately hoping that the next sort of $10 billion we spend on whatever finds something drastic and epoch changing to warrant even looking even further. Because if at some point we just keep finding out that actually we're doing pretty all right as we are, it's going to take a lot of wind out of the sails for the sciences, especially physics, particle physics and astronomy. However, it's not going to be the end of those sciences. There's still an awful lot you can do with the facilities we have, as long as we have funding to keep those going. It's pushing through to the next level of stuff that I really don't know. In terms of theory, it's really hard to know, because we had the most exciting theory for the last 3 decades has been string theory. And it's really, really clear now that it's, at least the optimism is gone. It might turn out to be a wonderful thing, but the voices which say, maybe it's right, but we're not going to know. And a lot of the promise is sort of petering out there. I'm not any sort of particle physicist, so I'm just sort of looking on from the outside.
Yeah.
It's just hard to know.
Well, string theory is a whole nother topic, and there's some great books written on that topic. Not Even Wrong, and the one by Lee Smolin, I can't think of the name, but it's
Trouble with Physics, I think.
The Trouble with Physics. So in closing, we have to go to the big question, and you have a debate with your co-author, Geraint Lewis. where does, on the G word, and what is your, what does this say? What does fine tuning in your mind say for those who want there to be a God? I mean, where do you come down on that? And if you want to be agnostic about it, fine. But I have to ask you the question, because the name of the show is Conversations Beyond Science and Religion. So we're going beyond. But anyways, where do you come down for those who are looking for something in this fine tuning debate?
Well, so
What does it
apart from
mean?
being agnostic, I was a theist before I started looking into fine tuning. So
Yeah.
it's not that it changed my mind about anything. Part of the reason I was interested in it was because it was something that even very hostile atheist physicists like Fred Hoyle that started saying very weirdly theistic things
Yeah.
about it. There's a wonderful quote from Freeman Dyson, who's another great physicist of the 20th century, in Scientific American in 1970, which is remarkably early for this one. He says, when we look at the way something like, when we look at the way all these different properties of our universe together, quote, it almost seems like the universe must have known we were coming.
Yeah.
Which very, very teleological kind of statement there. So, but I was a theist already. For me, it sits very neatly with what I already believed about the world.
Right.
And if I try my best to put myself in the shoes of specifically a naturalist, someone who thinks that natural stuff is the only stuff, there's just the universe, space, time, matter, and that's it.
Right.
That's all that really exists. If I try to put myself as honestly as I can in their shoes, I think this would keep me up at night. I think it would really bother me, because it seems like here's something which you would not expect on naturalism, but you very much would expect on theism. It's, there's no deeper reason for the universe on naturalism, so it better not look like there is some sort of deeper reason. Like, you mentioned before, Fred Hoyle, super intellect has monkeyed with physics, he says.
Right.
It better not look like that, and for all the world it does. Now, you can try to add to the stories in ways that take away that appearance, like the multiverse, but it's clear what you're doing at that point. You're sort of in the state that theists were, say, 100 years ago, when Bertrand Russell was trying to say, look, the universe is just an accident, we're accidental collocations of atoms. That's everything that science and physics has told us. And I guess if you're a theist back then, you could say, oh, well, maybe it looks that way, but maybe what we don't know will overturn that impression at some point. Maybe in spite of that impression, there could still be a God somehow. And now that story is totally flipped. It's that the first impression is of design and teleology and purpose, and you have to try to think about multiverses and all that sort of stuff to try to overturn that first impression. So again, I can't claim to be completely unbiased, but I am, as I try to think these things through, I think that generic, the universe is just an accident, we're just some typical third rock from the sun in some average galaxy, so desperately trying to say that we're average and normal, and fine-tuning just blows all of that at the deepest level of physics, just blows it all right out of the water.
Yeah, and that is my, that's my conclusion as well, because I mean, you got to go where the evidence leads, and if the evidence leads to whether it's spirit, intelligence, God, whatever word you want to put on it, then that's where the evidence leads. And I'm I think that's practicing science. And when I asked a question about 25 years from now, I'm thinking that maybe there'll be more people thinking like you and opening their mind to this possibility, because I think that you could be logical, rational, and come to this conclusion. In fact, I think, be honest, I think that it's a more logical, rational position to come to than the alternative, because I think the multiverse is a quote unquote cop out. No offense to folks who believe in it. And it's sort of like, it's like a Ruth Goldberg device. How many different little, touch ups or add-ons are you going to put on to like have your model survive? And at some point, maybe it all comes tumbling down. This is Philip Comella. This is Conversations Beyond Science and Religion. Luke, it's been great talking with you on this very deep and interesting topic. We didn't cover everything, but I think we covered enough to give the listener an idea. And I want to encourage folks to go out and pick up a copy of Luke's book that he did with Jarrett Lewis. It's called A Fortunate Universe, Life in a Finely Tuned Cosmos. And it is, what I think makes this book different is that it's an entertaining read. And Luke, you and Jarrett did a good job of keeping your senses of humor as you were writing this book, and which is hard to do probably, but with these topics. But the bottom line is that this is a topic that will not go away. It's fascinating, and it's a good way to sort of introduce yourself to the mysteries of science. This is Philip Comella, Conversations Beyond Science and Religion. Thank you for listening.